All right, so we'll be moving from talking about individual atoms and how the electrons are arranged on those atoms to talking about molecular compounds and how the electrons are arranged within the compounds. So the learning objectives for this segment are going to be to list the three principal types of bonds and explain what they are, predict which ionic solids will have the largest lattice energy, describe why lattice energies alone is not sufficient to determine the energetic favorability of ionic solids, and be able to compute components of the Born-Haber cycle. Okay, so there's three main types of bonds. Now, there's a lot of exceptions and things that are sort of on the borderline, but the three main ways to think about bonding are ionic bonds. We talked a little bit about that, and those are generally between metal and non-metal atoms. We talked a little bit how metal atoms are generally want to give up their electrons. Non-metal atoms want to take on electrons, and so that works pretty well. The metals get rid of the electrons, they go to the non-metal, and you have ions, and those form ionic compounds. So covalent compounds are usually between non-metals and non-metals. Since they don't really want to give up their electrons, but they also like electrons, they share the electrons. Very, nice of them. And we'll be talking a lot about that in that sense. There's lots of different ways that electrons can be shared between two or many atoms. And finally is a metallic bond. You might have heard of this a little bit less, where you have happens between metals and metal atoms. And usually what you have is essentially all the electrons are shared. The metal atoms like to give up the electrons, but don't have that strong an affinity for them. So essentially all the some of the valence electrons sort of drift back and forth between all of the atoms. And that's why metals are electrically conductive, because the electrons, rather than being bound to just one atom, surf around the entire surface. So that's that is how the bonding occurs there. They're all sort of in this sea of electron jello that holds everything together. It also explains why it's a little easier to bend and mold metals, is because as the atoms slip by, they don't have to actually break bonds. The bonds just sort of change as the sea of electrons changes shape. So that is so those are the three main categories. Obviously, there's things on the edges of all of these, but all of these are about how atoms stick together by doing something with their electrons. Okay, so first we're going to talk about ionic bonds and the formation of ionic solids. That's actually a little simpler in terms of what the electrons are doing, but it's because it's pretty straightforward. Here we have a sodium. We see the electron configuration there. And you've got a chlorine here. We see its electron configuration. And from what we know about periodic trends, that 3s electron comes off pretty easily. And the chlorine would really like to have another electron to fill up its n=3 orbital. So it seems very natural to have a sodium plus and a chlorine minus. And so now they both have noble gas configurations. Those are quite stable. And so let's see. So we want to form sodium chloride. Let's actually look at the numbers. We say, hey, the sodium wants to give that up. The sodium wants to give up the electron. The chlorine wants an electron. Hey, everybody can be happy. Let's put some numbers. So what we see is that the first ionization energy of sodium is about 496 kilojoules per mole of electron being pulled off. And the electron affinity of chlorine is about minus 349 kilojoules per mole. Wait a second, that's 147 kilojoules per mole. That electron doesn't actually want to jump. What gives? We know that sodium chloride forms. If you have sodium and you have chlorine gas, those are quite reactive. You get sodium chloride. What's going on here? And the answer is, it really depends. You have to look at the phases. Here, the electron affinity and the ionization energy are for a gas of the ion. Now, clearly, if you have sodium metal and chlorine gas together, that is not the same as a sodium atom in the gaseous form and chlorine in a gaseous single ion. That lack of wanting to move over is just because of the phases that we're in. What we need to do if we're interested in, well, I want to make sodium chloride, I want the heat of formation from sodium chloride, I want to make sodium chloride from its constituent elements, we have to actually look at the energies to move all the different atoms around. So This is the idea of the Born-Haber cycle. The Born-Haber cycle is, pretty straightforward. It's really just another restatement of Hess's law in the context of forming ionic solids. So the net reaction we're interested in is if we're looking at heats of formation is sodium solid. That's the most stable form of elemental sodium at one atmosphere pressure, 25 degrees C. Half a mole of chlorine gas. Chlorine gas is Cl2, combined to form sodium chloride. That is favorable. Sodium chloride likes to form. And so that's the net reaction that we're interested in. So what we need to do is construct a cycle that tells us how to get from one place to the other in terms of steps that we can describe easily. So first thing we have to do to get from sodium metal to sodium gas, that's pretty straightforward. We have to evaporate the sodium metal. That's an endothermic process. You have to put energy into that for it to happen, obviously, to go from a solid to a gas. Then also we need to disassociate chlorine from its from the diatomic chlorine into gas. That costs some energy as well. That's endothermic. And then we will need to take an electron off of the vaporized sodium, a neutral sodium, to make sodium ion plus an electron. That also costs a lot of energy. Then we start getting the energy back. So first of all, that electron likes to go to the chlorine. And so once it's free of the sodium, then it definitely is going to stick onto the chlorine. And then finally, we have the lattice energy. If you have gaseous sodium ion and gaseous chlorine ion, they're of opposite charges. They, of course, want to stick directly to each other. And you get a huge exothermic process. A lot of heat is released to get sodium chloride. So by Hess's law, that basically says that if we want to do this reaction here, we can do it by any other process. And here's another process. This is a process that gets there. It's a Born-Haber cycle because all of this together, takes it from one point and gets it back to the same point. But we're going through this particular set of reactions, which are things that can be determined relatively easily. In practice, you might find out the heat of formation, then use that to find out these quantities. But these are all quantities that are related together and helps explain, how we get highly stable ionic solids and how where the electron transfer takes place in all that process.